All right, we're going to look at how we develop models, and translational and rotational models are generally quite frankly, very simple. Uh, so we're going to model them based on the sum of forces equals ma. All right, and the way we do this is we need to write a full equation for each mass. All right, so we're going to have a sum of forces equals ma for each mass in the system, or each distinct mass that we model. Okay, I should say, like, for example, from a pragmatic point of view, or, well, from reality, when you look at dampers and springs, they have mass, but we will ignore their mass. So therefore, we don't have to write an equation, a mass equation for them. Okay, so for every mass that you model, you need a separate equation. Uh, Again, springs and dampers here are massless. And the way we do this is what I call the push-pull method. All right, so, and what that means is you take turns holding one mass still and move the connected masses to assess the resulting forces. What does that mean? Well, let's just look at this here. So what we'll do is when we go to model mass 1, what we'll do is we can do this in any order, but basically we're going to have to move mass 1. So what we do is we hold mass 2 still, we move mass 1 in a positive direction. Now this is a force in a positive direction. That's just plus F. We don't have to worry about it. We move this in a positive direction and say, what does it feel because of that? Well, it will feel opposition from this spring. So we move this plus K1, it'll feel minus K1X1 back, and minus B1V1 back. Because I move this way, these will oppose it. And that's all we have. And then to finish this, so to get the model for this mass, we hold this one still and move everything that's connected to it. Well, that would be mass 2. And as we move mass 2 forward, that will push this mass forward because of K1 X2 and B1 X2 dot, or V2. All right, and that'll give us the model for this. To model B2, or M2, excuse me, the second mass, we will hold mass 1 still and we'll move M2 in a positive direction and say, what does it feel? It feels K X2 going back. It feels B1 V2 going back. As this goes forward, it feels K2 X2 going back. It feels B2 V2 going back. After that, we hold this one still and we move all the masses connected to it. Well, that's this one. We move it forward, and the M2 will feel a K1 X1 pushing it along and a B1 V1 pushing it along. So that is my push-pull method. Now, I'm not actually pulling anything, but that's not important. All right, so if we apply that here on mass 1, in this case, hold mass 1 still, move 2, which is connected to it, and say, what does M1 feel? So we move this in a positive direction, and M1 will feel K1X1 and K1X2, because this moves in a positive direction, X2, and B1X2. And all of these over here, M1 doesn't feel that. It only feels the result of M1 moving and what comes through this spring and that damper. So then we hold M2 still and move M1 in a positive direction. It has the force F, so we just add that on, but then it'll have opposition from K1X1 and B1X1 dot. And it's all done. All right, and we do M2. We'll hold M2 still, move X1, and M2 will feel K1X1 pull it along. It'll feel B1X1 dot pulling it along. Then we hold M1 still, move M2, and say, what does it feel? Well, it'll feel opposition from K2X2, K1X2. It'll feel opposition from B2X2 dot and B1X2 dot, and these are all here. And of course, we can then just regroup things in this way. And this one, I forgot to add in, equals 0. And we brought everything to the other side. Now I'll note you can have the x1s here, and if you bring the x2s over, you would then have plus b1 x2 dot plus k1 x2. So you'd have this would act like an input relative to that. And if you bring the x1 stuff onto this side, then the x1 would act like an input relative to that. Anyway, group them however you want. That's just an algebraic thing. All right. We have one other thing we have to kind of deal with a little bit, and that's the effect of gravity and how we're going to handle that. And we have a choice. So let's start setting that up. So here we have a mass spring damper system. So we got a mass hanging down. There's a spring and a damper holding it up to the ceiling. We have a force that we can apply to the mass, and there's obviously going to be gravity. All right. Since we call those massless, we don't have to worry about gravity on them, but we do on this one because we're modeling it as a mass. All right. If I move this mass in a positive direction, it will feel this pulling it back and this pulling it back. So we'd have mx double dot equals force coming down, mg going down, and note I'm measuring positive down, and then I'd have a minus kx1 minus bx1 dot. This is just brought to the other side. Now, it's important to note here we said I'm setting up a coordinate system measuring everything from the unstretched position. So somebody's kind of holding this up. The spring isn't stretched. Don't have to worry about stretch on the damper. Okay, so I'm measuring from that point where the spring is unstretched, and then we let it go. All right, so the 0 is the unstretched position. And so if we think about what's happening, let's just let the force be 0. So we're going to let F be 0 for the moment. mg is forever constant. As long as this mass is whatever this mass is, it's mass times gravity, doesn't change. It's forever. All right. If I let this system go to steady state, there's no force here. All we have is the influence of gravity. I release the system, so it goes doing. It'll reach a steady state. When that happens, the force in the damper will be 0 because there's no velocity. So what's going to happen? You're going to have some k times some x stretch that this spring stretches, as measured from here, equals mg. They'll cancel out. They always cancel out. All right? So we have that. And this brings up a point. Suppose we were to measure x, not from the unstretched position, but from the stretched position. So static equilibrium, when the gravity and the spring are in equilibrium. So here is the unstretched spot, here's the stretched spot. Well, it turns out, when we do that, then these would cancel out and we could actually ignore the gravity. Okay, we could ignore this. Let's see where that comes from. All right, so here's the original differential equation. It is true. So here our x was measured from the unstretched position. So what if I were to now say, well, I'm going to measure everything. I'm going to create a coordinate system x hat that is measured off of here. So we have x hats going off of this spot. Well, then relative to our previous coordinate system, we'd have mx double dot bx dot plus k x stretch plus then this perturbation off the stretched point. All right. Well, so now I have mx double dot plus bx dot, then I have this k stretch and the mz. Well, those cancel each other out. This equals that. And then we have our f left over. So now I have a differential equation, mx double dot plus bx dot plus k, this x hat, measured at the stretched point. And now here's what I want you to, let's take a notice of this. What is x double dot? Well, let's just deal with x dot. X dot is the derivative of x, measured from our original spot, which is the derivative of x stretch plus x hat, our new thing. But this is a constant. So when I take the derivative and distribute it to this and that, derivative of x stretch is 0. And so what we have then is here's x hat dot equals x dot, which means x hat double dot equals x double dot here. So I can rewrite my differential equation as mx hat double dot. The hat simply means I'm measuring it from the static equilibrium position where the spring is stretched. Bx hat and kx equals f. This is called the dynamic ordinary differential equation. All the static effects that are forever constant have been canceled out. All right? And if you do that, if you measure things from the static equilibrium position, so you just let the mass hang, let this gravity and spring just kind of negotiate their settlement. If you do that, you can ignore the gravity. And you're just measuring everything off of that static equilibrium position. If you're using mg, this is now a static and dynamic ordinary differential equation, and there's no need for it. So that's how we will generally do things, but we need to do a little practice to get a handle on this. So we'll do another problem here. I think next, yep, where we'll play with this concept one last time. See you then.